this is lecture 19, linear algebra, general vector spaces, and linear independence. Again, another important definition, we say that the set S of vectors u1, u2 up to um, a subset of V, vector space V, is a linearly independent set if no vector in S can be written as a linear combination of the others. Well, let's see. It means, for example, this U2 cannot be written as a linear combination of, say, U1 up to UM without the U2. So, if I take U2 is not equal to any linear combination of the others, right? So this cannot be a linear combination of the others for any scalars k1 to kn. Okay, so, well, this is not easy to check. If a set of vectors is given to you and you are supposed to find out whether it is linearly independent or not, it's not easy to check. But sometimes it's not that hard. I mean, let me give you an example that can be shown using this, in fact. So, this is like a typical example when we solve systems of equations, we reach this point. So this example is like this. You might have seen when we find, say, general solution to a homogeneous system, those vectors, those column vectors, after some point, the entries are like 1, 0, 0, 0, 1, 0, 0, 0, 1, and so on. So let's say, example S, let's write it like this. Say minus 1, 2, 1, 0, 0, say 3, 5, 0, 1, 0, and the third one minus 10, minus 102, 0, 0, 1. Okay, let's look at this. Can this be a linear combination of these two? So let's write it. Minus 1, 2, 1, 0, 0. This is question mark. Now if I multiply some k1 by 3, 5, 0, 1, 0 plus some k2 times minus 10 minus 102, 0, 0, 1. I don't care about the other entries. Whatever these entries, I don't care. But what happens to this entry? This guy here. The third entry and the third entry. K1 times 0 plus K2 times 0 is 0. And the rest I don't care. So if I use any two scalars, I will never ever get anything but 0 in this location, the third entry. But the third entry here is 1. The third entry here is 1. So this can never be equal to this. Can never be equal to this. Because the third entry here is 1, here it is 0. And this can never be anything but 0 because of these two, and this is 1. By definition, it's 1. So these two can never be equal. And you can check for the other ones, like if you take this one, this has 1 here, this has 0 here, 0 here. So if you add them with any coefficient, you will get 0 here for these two, but it is 1. And the third one. So this, in fact, kind of we can say, you can even in general say that this happens if after a certain point, like entry, so you might have like 10 entries here, and then the 11th one to the end is like this: 1, 0, 0, 0, 1, 0, blah blah blah. So the one jumps from here to here to here to here to here to here. So each one of them has the one at a different position. So if that happens and the ones are at different position after certain level, then that set is linearly independent, and you can just write down the same logic or the same argument for those. And that is what usually happens when you solve a system of equations the way that we do it. If you take those columns with that do not have a leading one as free variables, then this happens. Okay. But there is also another way to show linear independence, and that's the theorem. That theorem is this. So let me. And that's important theorem. S is U1 up to UM as a subset of V is linearly independent if the equation, remember this is like an equation, K1 U1 plus K2 U2 Km Um equal to 0 has only the trivial solution. I.e. K1 equals K2 equals equals Km equals 0. Now this is an equation. Remember I wrote down AX equals B in this format. So it's like this system of equations. So you might have U1, column number 1, column number 2, up to column number M, say, and this is multiplied by K1 up to Km, and that equals 0. So this looks like this. So this system of equations has only trivial solution. Okay, so this system of equations, this is equivalent to this, has only trivial solution. Well, so what it means is to show that they are linearly independent, you have to solve this. You have to solve this system of equations. But sometimes it's very easy. Let me give you an example, which is in fact the example I gave you. So let's do that using this fact. And it's very easy to prove. If say one of them is not 0, say if one of them is not 0, then you can write that one as a linear combination of the other ones. So it is. So it is apparent that all of them should be 0. When all of them are 0, you cannot write any of them as a linear combination of the other ones. That's in fact the meaning of this that we are saying. You can just think more about this if you like. Otherwise, we usually don't. In fact, what we use this thing is just proving some theorems, and then we use those theorems. So let me give you that example. Again, let's go back to that example and see what it looks like using this. What was this? I can't remember the number, so just let's write some numbers here again. 2 minus 3, 1, 0, 0, and the other one was, I can't remember, 10, what was that, 1 and 2, 0, 1, 0, and the third one, minus 5, minus, say, 10, minus 12, say, 0, 0, 1. Okay. So, let's multiply K1 times the first one, K2 K2 times the second one K3 times the third one. And then equals 0, 0, 0, 0, 0. Right? So let's put them together. Well, I don't care about this. This is in fact 2K1, 10K2, blah, blah, I don't care. And the second one, I don't care. But the third is K1 plus 0 plus 0. Then it is K2, 0 plus K2 plus 0, then it is K3. Right? Let's look. This is K1, 0, 0, 0, K2, 0, 0, 0, K3. And this equals what? 0, 0, 0, 0, 0. So what will you get out of this? So you will get K1 is 0, K2 is 0, and K3 is 0. So that's it. I don't care what these two are. When K1, K2, K3 are 0, you can see that the first row is also 0, the second row is also 0. So if I have this combination 1, 0, 0, 0, 1, 0, 0, 0, 1, then whatever the rest of these vectors are, those vectors are linearly independent. Because a linear combination of them, when set equal to 0, will give me only 0 for coefficients. Only. So the solution of this is in fact 0. Now, you might say, what kind of a system of equations is this? Yeah, this is this system. Look, 2K1 plus 10K2 minus 5K3 is 0. The second row is minus 3K1 plus 102K2 minus 12K3 is 0. And then the third one is K1 is 0. The other one is K2 is 0. Then K3 is 0, right? This is a consistent system with 0 solution. So this is this. A consistent system with only 0 solution because of these three. So this is consistent. You just put 0, 0, 0, you get 0. Okay, so that's a nice example of and I'm emphasizing on this kind of example because we will see we need a solution space or solution set of a system of equations to be generated by linearly independent vectors. And when we solve them using the method we have developed, you will get vectors like that. So let's go to other things here. So, first of all, there are certain things. If you have a 0 vector in a set, that is not linearly independent. So let me write down some facts which you can prove. 1. If S includes 0, then it is not linearly independent. Why? It's very simple. You just write k times 0 plus 0 times the rest of them, and this is 0, and this is not a 0 combination. You see, this k is not 0. It doesn't have to be 0. But any k times 0 will give me 0. The rest of them can be 0. But this is one of them which goes with 0, then will give me a non-zero solution. The next one is it is in fact for 2. Sometimes we see if S has 2 vectors, say u1 and u2, then S is linearly independent if none of them, if U1 cannot be written as some K times U2, right? For some K. Some non-zero. Okay. This makes sense because if you can write it as this, then U1, 1U1 minus K U2 is 0, and this is what? A non-zero linear combination. So if this is linearly independent, this cannot happen. Okay. And the zero set with just zeros in independent. We just assume that it is. So we usually don't encounter things like that so extreme. So let me and again another important theorem, very important this one. So a subset of Rn with say with more than n vectors is not linearly independent. This is crucial. Example. Just let's say S is just dimension 2. 1, 2, say 3, 5, for example. And the third one, 100 to 221, something. This is not linearly independent, not linearly independent. And look, this is a subset of R2, right? These are elements of R2, so that is a subset of R2. And we have 3. This 3 is bigger than 2, right? 3 is bigger than 2. So if I have like 101 vectors in R100, that set is not linearly independent. What does this mean? It means that without doing anything, we can just say that this is this one plus this one with some k's. We can say that. We can say that anything like this is consistent. So this, if I write something like this, you see these theorems can give us amazing results. Without proving something, we can say that any, say 1 x1 minus 3x2, that's the first row, equal to 100, and the second one is 2x1 plus 5x2 equals 221 is consistent. Well, I guess there's something, because these two are in fact linearly independent, these two. Otherwise, I wouldn't say that. Because then you will get 0, and in fact, if they are not linearly independent, then let me think. If this is in fact multiple of this, then you have, in fact, two vectors, not one vector. But anyway, so let me think about this already. Well, exactly more. What happened there? Well, there's one thing. Oh yeah, true. So if this is a multiple of this, then I don't care about that one. Then these two give me a subset which is non-linearly independent. So if a subset of this is non-linearly independent, the whole thing is not. But if this is linearly independent, then you can write this one as a linear combination of these two. That's what happens. So if I can find a subset which is linearly independent, then like in this case, I can write this one as a linear combination of vectors in the other one. Well, so yeah, that makes sense. So this is true for any situation, even if one of them is multiple. So that is yeah, and also linear independence in function spaces. We need this in the next part of this course, and that is the differential equation. So, linear independence in function spaces, and that is, say, if I have, say, n given functions, f1, let's use f1 or something else. Yeah, okay. f1 and f2 up to fn, and they belong to C. I just need n minus 1 of minus infinity and infinity, which means they can be, say, differentiated n minus 1 times. So let's see, how can these be linearly independent? Okay, so let's write the K1, F1, let me, okay, that's okay. So K2, F2, and K and Fn, and this 0 is 0 function, so 0 is 0 function. Okay. Now I can differentiate this n minus 1 times. So I have k f1 prime, k2 f2 prime, kn fn prime. Then k1 f1 double prime, k2 f2 double prime, kn fn double prime equal to 0 again. 0 prime is 0. And k1 f1 n minus 1, this is n minus 1 primes, plus k2 f2 n minus 1, and plus kn fn n minus 1 equal to 0. I didn't write x here, so I'm just I'm saying that these are like functions are like entities, as I said, they are elements of a set. You don't have to write x here. And the derivative of this function is another function, so that's also an entity here. So, well, how many equations do I have? N equations. Remember, this is like 0. 0, 1, up to n minus 1. So I have n equations in n unknowns, right? I want to see if kn's will be 0, all of them. If the kn's or ki's are all 0, then the fi's are linearly independent. So let's put this in a matrix format, okay? So let's put this system of equations in matrix format. Let me erase this and put this in matrix format. a matrix format where the matrix here is F1, F2, Fn, F1 prime, F2 prime, Fn prime, and this goes to Fn, n minus 1, F2, n minus 1, dot, 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 Fn, n minus 1. And I have a case here, K1 up to Kn, and here I have all zeros. Here 0, dot, 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 0. So this is n equations and n unknowns, n by n. So how could this have 0? Just 0 solution. If this has 0 solution, then the fi's are linearly independent. Remember that ki, k1, f1, k2, f2 equal to 0. If this has 0 solution, only 0 solution, then the ki's are 0. And that's the condition for linear independence. But how could this be 0? It has only 0 solution if the determinant of this is not 0. If the determinant of this matrix is not 0. So, and let me erase this and say that the determinant of this matrix, if the determinant of this matrix is not 0, then ki's are 0 for Ri, which implies f1 up to fn are linearly independent. And we say this is not identically 0, which means this function might, this determinant might be 0 for certain x's. Identically means it is 0 for every x, but it might be 0 for some x's. And as we will see in some situations, it might be 0 for some x's. So let's see. Now this determinant has a name. This determinant, this guy here, this determinant is called Wronskian of FIs. It's denoted by this. So this determinant is denoted by this, and we say it is not identically. So let's write here identically. Okay, so let me give you an example. So the two interesting and familiar functions from example. S equals sine x, sine theta, and cosine theta is linearly independent. Now what does this mean? It means that if I write k1 sine theta plus k2 cosine theta identically equal to 0, this means they are identically 0. Then the only way that this can happen is that k1 and k2 is 0. You can just, that's intuition. So if this is 0 for, say, every theta, I can put, say, 0 for theta, then sine 0 is 0, cosine 0 is 1, so k2 is 0. Then also here, if I put pi over 2 will make this one 0 and this one 1, then k1 is 0. But let's check the Wronskian. So the Wronskian of sine and cosine at theta. Okay, that's how we write it. So that is determinant of say it's better to write cosine first. Cosine theta, sine theta, you see why. Derivative of this is minus sine theta. Derivative of this is cosine theta. So determinant of this is cosine is cosine square theta minus sine minus is plus sine square theta, and this is 1. And this Wronskian is 1 is not 0, so and is not it doesn't depend on theta, but it might depend on theta, but it's not 0 at all, not identically at all. So we say that they are linearly independent. So S is linearly independent. Okay, we will see this linear independence when we solve second degree linear differential equations. Okay, so that is in fact the story of linear independence and linear independence for say functions. So let me stop and continue with the next section some other time.